So now we can solve all 1D and 2D problems.
So we will start chapter 12, sorry, class 12, sir.
Yeah, today we'll do that.
Okay.
No, the class 11. So 1D problem 2, all questions you can solve.
I sent you one problem, sir. In that first problem was a little complex.
Okay.
Can you have any trick?
And okay, the 2 snaps which is in that thing is clear.
Yes, sir. But first snap was too long, sir. That's the problem. Solution was
okay. So I'll come back to that later. So we'll do with the today's topic.
okay.
Your laptop is ready now?
No, sir.
Tomorrow?
Ma.
Okay. So we'll start now.
Okay.
Okay. So these things you know, right? Charge. And what is meant quantization of charge? Why do you say charge is quantized? Because when you have to charge, you have to remove electrons, right?
Yes, sir.
In general, for a conductor, for charging, you have to remove electrons or you have to add electrons. Okay, an electron has got some amount of charge, finite charge, 1.6 into 10 to minus 19 coulombs. So, but you cannot remove fraction of charge.
Yes, sir.
Okay, so that's why the charge of a body can be either 1 electrons or 2 electron or 3 electron. It cannot be 1.5 electron or something like that. So that is called quantization. Quantization means there will be some discrete jumps in the values. Okay, Coulomb's law. Okay, right. So this is a general picture of an atom where the nucleus is there. Inside the nucleus there are protons, and what is the red one?
So you didn't share your screen.
Sorry?
You haven't shared your screen yet, sir.
Oh, okay. Okay, now you can see.
Yes, sir.
So this is a picture of an atom. So in the central part you have the nucleus. So this positive is what proton, and what is the red one?
Nucleus. Neutron.
Neutron. So they form the nucleus and they form a very tiny region. After there is a large gap, and then electrons are there. So this is a general picture of an atom. Okay, so if you have to charge a body, you have to remove the electrons from the outermost shell, or you have to add electrons to it. Okay, so when you remove an electron, you'll get a negative charge, positive charge of plus E. If you remove 2 electrons, you'll get a positive charge of plus 2E. So similarly, if you add an electron, you'll get a negative charge of minus E. Okay, so you cannot remove a fraction of an electron. So the charge this can be added is only in steps of E. Okay, so it cannot take continuous values. For example, if you draw a number line, the x-axis it will take continuous values, right? You can draw any value on the x-axis, but here the value of the charge it will not take any continuous value. It will have only values in steps and steps of E. Okay, this is Coulomb's law. So Coulomb's law, we have 2 charges. So what is the charge? What is mass of a body?
Sorry, sir.
What is mass of a body?
Amount of substance.
Yeah, something like that. So what is charge then? Mass is like a property of a body by which it will experience a gravitational force. Okay, so similarly, charge is a property of a body by which it will experience a electrostatic force. Okay, and there are similarities. Both of the forces will go as 1 by r square, and it's also depend on the product of the charges. There will be product of the masses, and there will be a constant. Here, in the case of Coulomb's law, the constant is k, or it's 1 by 4 pi epsilon naught, and the value is 9 to 10 to 9. In the case of gravity, what is the constant called? What is the symbol?
Capital G.
And what is the difference between the electrostatic force and gravitational force? One major.
Gravitational force is always attracting, but electrostatic force can also be repulsive.
Yeah, and the similarities both are 1 by r square. Okay, and the force is a vector, so it will be along the lines on the two charges. Same for gravity also, but here they will be repulsive or attractive depending on whether they like or unlike. So these things you know. So whatever things you know, I'll go a little bit fast. So if you have Coulomb charge deals with 2 point charges, right? So force between 2 point charges. So if you have the third charge, okay. So here in this picture, how many charges are there? 1, 2, 3, 4, and 5, right? 5 charges are there. So if you have to find force on any particular charge, say the first one Q1, do the remaining 4. How do you do that?
Superposition.
Yeah. So you can take one at a time. Always Q1 will be there because you're going to find force due to Q1. So you take Q2 and find the force due to it, that is F21. Similarly, Q3, F31. And the another important thing is, suppose these 3, 4, 5 charges are not there. So the force due to Q2 will be F21. That is the same value of the force in the direction of the force that will be there when I have these additional charges. You get that point? The value of the force Q2 on Q1, which is F21, its value and direction will not change because of the presence or absence of the remaining charges.
Okay. Yes.
Okay. Suppose, for example, if this is 5 Newton, just because I have a third charge, this value of 5 will not change. It's independent of whether this. So basically, you have to assume that other charges are not there and then find F21. Similar to find F31, you just assume other charges are not there. So F31 is as if it's only due to Q3. And then you have to add these 4 vectors vectorially. Okay, for that you can add 2 vectors at a time and then get the resultant vector. So this is called principle of superposition. That's what I said, individual forces are unaffected by other charges. So for all the electrostatic problems you can solve by, these are the basic ideas, Coulomb's law and superposition principle. So if you use these two, you can solve any problem. So
Yes,
did you look at the notes which I sent? It's in your folder. So this problem you understood. The charge Q is split into 2 parts. So the electrostatic force between them will be maximum if they are split in a certain way. So find charge of each part for maximum force. The distance between them is fixed. Okay, let it be some distance d. But the way I'm going to split one of them, say it's small q, the other will be capital Q minus small q because the total charge is conserved. Like mass is conserved, so charge is also conserved. Only then I can split it into 2 parts, but the total sum should be same capital Q. Okay. Now what is the force between these two? It's begun with Coulomb's law. So this expression is clear.
Yes, sir.
So what is the only variable in this expression?
Small q.
Because capital Q is the total charge is fixed. So this function of Q, and it's a quadratic because Q square is there. And the coefficient of
Yes.
Q is negative. So it will be inverted U. Equation of parabola is U. If the coefficient of second degree, that's Q square here, is negative, it will be inverted U. And the roots of the parabola are Q equal to 0 and Q equal to capital Q. So 0 and capital Q. And by symmetry, the parabola will have a maximum at the middle. So that will be at Q equal to Q by 2. Is this clear?
Sir, we can differentiate, sir.
That also you can do, but this will be quicker. Whatever is convenient you can do, but while learning in the home, you learn by multiple ways. In the exam, you just do whatever is shortest for you. Okay. So it will be maximum in the middle. So if you get the maximum force like this. Is this clear?
Yes, sir.
So 4 charges, Q and minus Q are in the corners of the car. So find force and capital Q placed in the center. Okay, so here you have to use the superposition principle. So, but we can simplify things depending on what is there in the problem. So if we take these two charges together, those forces will cancel, right?
Yes, sir. Exactly opposite.
Yeah. So I have to take force due to this one. So it will be in this direction, and force due to minus Q, that will also be in this direction. And the value of the force will be the product of the charges Q into Q divided by the distance square. And the distance between Q and Q is A by root 2. If the side of the square is A and this is also A, so the full diagonal will be how much? Root 2A.
2A.
Root 2A. A square plus A square square root.
Okay, yes, sir.
So root 2A. So half diagonal will be root 2A divided by 2. Right? Half
Yes, sir.
diagonal will be A by root 2. So the distance square is
Yes,
A by root 2 square. And two of them are there, and both the force values are same. Only the direction also same. That's why they're adding. So this is clear?
I have a doubt, sir.
Yeah.
The magnitude of the charges are opposite, sir.
No. So one is minus Q.
want...
One is minus Q, so it'll be attractive, right?
That is fine, sir.
Huh.
But if we add these two forces, means won't they get cancelled, sir?
No. See, the force due to this small q is this one, this arrow. Okay. And force due to minus q is this arrow because it's attracting. So both these charges are trying to create a force in this direction, right? Both these.
Diagram I can understand, sir, but if you write it means.
No. Then you have to write with the vector quantity.
That's what I understand.
Then you have to put I cap and minus I cap. So minus of minus I cap will become plus I cap.
Oh.
Got it?
Mm-hmm.
Is it clear?
Can you do that one, sir? For understanding the question.
See, suppose I denote the unit vector in this direction as n cap. Okay, so the force due to this one will be Q into Q divided by the distance square R square. And the direction is what? N cap, right?
Yes, sir.
Okay, and the second one will be minus Q into Q by R square, and the direction will be minus N cap.
Why minus N cap, sir?
See, because force on this one. See, when you want to find force on this one due to this one, so I have to place this at the origin, right? So for this thing, the N cap will be, when I'm calculating this force, okay, so I have to, so this is a, I have to put one of the charges at the origin. So I'll put capital Q as origin. Okay, so in this case, the N cap for this one, the N cap direction should be this one. So I have to take N1 cap. And for this thing, I have to take this N2 cap, say. So the first one, it will be N1 cap, and the second will be N2 cap. Now it is clear. Okay, and N1 cap equal to minus N2 cap.
So that will be N cap only, sir.
No. See, capital Q is the origin. And the direction of this unit vector should be away from this capital Q. So for this force, I have to choose this unit vector N1 cap, and for this charge, I will choose this unit vector in this direction.
And it is like the plus x and minus x only, sir.
So this you have to understand. The unit vectors for both of them are different because they are in the opposite directions. The charge which is experiencing the force, you have to place it at the origin, and the unit vector should be away from that charge. So for this Q, you have to take N1 cap, and for this minus Q, you have to take N2 cap.
Okay. Okay.
So this way, you should not apply the formula blindly. Take the magnitude of the force and get the direction by using the physics.
Yes, sir.
Okay, so you have to understand the formula, not just apply the formula.
Okay, sir.
So it will become complicated if you do these things rigorously as a maths thing. So you have to understand and do it as a physics problem. So get the magnitude of the force, and then direction you fix it whether by light charges or unlight charges.
Yes, sir.
That will be easier. So here, force charges places the circumference of a dial clock, and okay, and Q0 is at the center. So there is a hover hand. So we have to find the direction of the resultant force. Okay, so Q0 and Q is positive, right? So there will be a repulsive force in this direction, and because it's plus Q, there will be a force in this direction, and because it's minus Q, there will be a force in this direction, attractive force, and because it's minus Q, there will be a force in this direction. Okay, so all these forces are equal forces because the product of Q0 and Q, the magnitude are same and the distance are the same distance. So 4 forces equal magnitudes, and these 2 forces are add, and these 2 forces are add. So if you have 2 vectors which are equal, the resultant vector in the middle, angle bisector.
Yes.
So it will be between, this is 6 o'clock, 7 o'clock, 8 o'clock, 9 o'clock. So it will be between 7 and 8, that is 7:30. So correct option is option B.
Yes, sir.
Okay, this is just summary. So now we have to introduce the concept of electric field. Previously, we just had a concept of electric force between 2 charges because of the Coulomb's law, by Coulomb's law. So if we suppose I have a point charge, and what is the force of this due to this point charge and a unit positive point charge? That is called the electric field due to this source charge capital Q. So that we can get the Coulomb's law, 1/4 Q into 1 divided by R square into R cap. So we have to place this charge Q at the origin. Okay, and electric field due to this charge kept at the origin at a distance R is force on a unit positive charge placed at that point. Okay, so force experienced by a charge Q in the electric field is given by Coulomb's law. And this can be written as Q into E, where E is the electric field produced by the source charge capital Q, and small q is the charge which is experiencing the force. So the force I can write in 2 forms. One is by Coulomb's law, another in terms of electric field produced by the source charge. Is this clear?
Yes, sir.
Okay, so this is the concept of electric field. Electric field is basically the Coulomb force due to a charge on a unit positive charge. So similarly, if I have more than one charge and I have to find electric field at this point, so here there are 4 charges, Q1, Q2, Q3, Q4. So just assume only Q1 is present because I find the electric field like this, E1. So the direction of the electric field is away from Q1 because Q1 is positive, and this is a unit positive charge. That is the definition of electric field. So there will be a force of repulsion. So the direction of E1 is like this. Similarly, E2 will be away from Q2. So E3. So you have to add all these vectors vectorially. This is by superposition principle. Okay. So 2 point charges Q1 and Q2. They are located at points A and B. So what is the electric field at B due to Q1? Does this electric field depend on Q2? What is force on Q2 to Q1? Does this force depend on Q1, Q2? How is electric field and force related? So is the question clear? So here there are 2 points, A and B. And I put 2 charges, Q1 here and Q2 here. So how to find electric field at B? So what is electric field at B due to Q1? What is the expression?
Take Q2 by R.
This distance is R. Electric field is just the source charge by R square. It's actually Q1 into 1 because it's force on unit positive charge. So it's basically taken by R square. And what is the force on this B? That is force on Q2.
Take Q1 by R square.
No, force will become by Coulomb's law.
Okay.
K Q1 Q2 by R square. And this I can write as Q2 into E. So I can find the force on this charge Q2 either by using Coulomb's law, okay, or I can use the concept that the force will be the value of the charge into the electric field at this point. Electric field at this point due to the other outside charges. So electric field at this point due to Q1 will be this one into the charge value. So force I can get either by this thing or by this thing, where E is the electric field produced by the other charges on small q. So the electric field produced by this at point B will depend on the source charge only. It will not depend on Q2. But the force on this Q2 will depend both on Q1 and Q2. Calculate the electric field intensity, which will just sufficiently balance weight of the electron. If this electric field produced by second electron below the first, what would be the distance between them? Electron charge is given. Okay, so we understood the question.
Yes, sir.
Okay, so there is an electron, so it will have a mass, so it's on Earth, so there will be a weight acting on it, and I'm applying an electric field, and the direction of the electric field should be done. Force on a charge is QDE, right? In an electric field. Force on a charge present in an external electric field is QDE, and for an electron Q is minus E. So the direction of the force on the electron and the electric field will be opposite. So to balance this weight, I should have a force in the upward direction. So the direction of electric field should be downwards. Is this clear? Otherwise, the force won't act upwards. Because force is given as QD, where Q is the charge. For electron, the charge is minus E. E is a positive quantity. So the direction of the electric field should be downwards. Otherwise, it will not balance. Is this clear?
So if the electric field is downward, then electric force also will be downward only, sir.
No,
because that extra will...
That's what I'm saying. Electric force is given as a charge into the E, right? And what is charge? Charge is minus E for the electron. Okay, so this minus will, it's minus E D. So the direction of this thing is opposite to E, right? Direction of minus E.
Then minus E, then the force will act towards that charge only, sir. Then it will be downward only, in that case also.
What is the direction of minus E? Opposite to E, right?
No, sir. Minus E means negative charge only, no, sir.
E is positive quantity, right? It's given here.
Electron. You are just representing that electron as minus E, no, sir. Electron is negative charge only, no?
E is a positive value. It's given here, no? Electron is minus E.
Capital E, what talking about,
capital E is the electric field. What is
I'm
direction?
saying electron, sir. Electron.
What is direction of
In
I
that
cap?
point,
Direction of I cap is along
I
positive x-axis, right?
yes, sir.
What is direction of minus I cap? The full thing.
Negative x direction.
Opposite, right? So similarly, direction of E is along positive direction of E. Direction of minus E is along opposite to E. What is direction of 2I cap? It's positive x-axis, right? Direction of 2I cap is positive x-axis, right? Yes or no?
Yes, sir.
What is direction of minus 3I cap?
Negative x direction.
So similarly here, negative quantity is multiplying the electric field vector. So the direction of this whole thing is opposite to E. Another way to understand this one is to get the electric field. One way to get the electric field is I can have a capacitor plate here, right? And I can have the opposite capacitor plate here. So what should be the charge of this capacitor plate? Plus or minus? Direction of electric field is downwards. So it should be plus here, right? And minus here. Inside the capacitor plate, the electric field is from plus to minus.
Yes, sir.
So this electron will get attracted towards the positive plate or negative plate?
Positive plate.
So then the force direction is upwards.
Okay.
This is the basic thing you have to remember. Force on a charge placed in external electric field is QD. So if Q is positive, means the direction of force is same as the direction of the electric field. If the charge is negative, then the direction of the force is opposite to the electric field. Okay. So always the electron will try to move against the electric field. Your positive charge will move with the electric field.
Yes, sir.
Okay. So now this force balance equation you can write. The electrostatic force E into E should balance this weight. So from this I can get the electric field as this one. The values are given. Mass of the electron is this one. G is 9.8. So we'll get this answer. Now I have to generate this electric field using another electron at the Earth surface. So if you have a negative electron here, it will create a repulsive force. So this repulsive force will balance this weight of the electron. And the repulsive force is given by Coulomb's law, 1/4 E by R square. Okay, sorry. This electric field, whatever is the value, I can generate by this point charge. This electron will count. So electric field due to a point charge is 1/4 the charge divided by the distance square. So this expression should match this value. Only then this electron will be able to create the electric field required to balance this electron. So from this I get R as this one. 1/4 I can take it on the other side. This E value is known from this one. R is I have to find out. Electron charge is known. Okay, so everything is known here. Just have to find R. So R will turn out to be 5 meters. So is it clear?
Yes, sir.
So electric field lines. So what is the electric field line? But already studied, no?
It just represents the electric field.
Okay, so suppose this charge is positive. This is a representation of the electric field. So what is the difference that you're noticing from this arrow and this arrow? What is the difference?
That is a length, magnitude.
So why is it decreasing?
Distance increases.
Yeah, so electric field goes as 1/R square. Electric field
Yes,
charge Q is 1/4 Q divided by R square. So if R increases, the magnitude will go down. So the length of the vector is the magnitude, which will keep on decreasing. Okay, as you go at infinity, it will become 0, and the direction is radially outward. That is by Coulomb's law, right? This electric field is force on a unit positive charge kept here, right? So it's positive. This also positive. The force along the line of the journey, line joining the two charges, which is this direction, radially outward. So the direction of electric field is radially outward. And this vector and this vector, what are the difference? These two. Is there any difference or not?
No, sir. I don't find difference.
Directions are different, right?
Ah.
But the magnitude is same. So similarly, these two also, the directions are different, but the magnitude is same. So, okay. So once you can take any point and draw the electric field at that as a vector. Okay. So to get the field lines, you just have to draw a curve which is just touching these vectors. So that is this electric field line. So I have to draw a curve just which will have these arrows as tangents. So this is that curve. Is that clear? And this curve is called electric field line. In this case, the curve is a straight line. So that's what I've written here. Electric field is drawn such that tangent to it gives the direction of the electric field. So once I draw these lines, I can go from here to here. So at any line, if I draw the tangent, that will be the direction of the electric field. So if we draw a tangent here, the arrow can be either upwards or downwards, but the arrow I have already put here. So that will give a direction. So it should be outwards. And the size of the vector, that is proportional to the magnitude of the electric field, that is proportional to the density of lines. So the density of lines here, if you take as area, and the same area here, the area should be same. The density of lines cutting the area is decreasing, right? Yes. If you take a small area here, see, this is electric field vectors. These are electric field lines.
Yes,
so how to draw the lines is clear, no? You can take this as a starting point. Okay, this you can draw by Coulomb's law. And from this, we can get this one by drawing a curve which is touching these vectors. That is these lines. So from here, you can get this one. And magnitude of the electric field, it's indicated as if I take an area here, the number of lines cutting the area will keep decreasing if I take the same area outside.
Yes, sir.
Okay, so that's an indication of the magnitude is decreasing.
Yes, sir.
Electric flux means you have to define an area. So it is the number of, in some sense, it is the number of lines which is cutting that area. So if the electric field magnitude is more, then the number of lines cutting the area will be more, because while drawing the electric field lines, we will have a scale. If there are 2 lines, means it's 2 volt per meter. So if you have a scale while drawing the electric field lines, say I will draw 5 lines for 1 volt per meter. Unit of electric field is volt per meter. And so if the electric field is 2 volt per meter, okay, then the number of lines, I have to draw 6 lines. Okay, so if you have an area, what?
We should not draw 10 lines, sir.
No, that you can fix for 1 volt per meter. If I, oh sorry, I made a mistake. That's 10 lines. This is just a scale. Suppose instead of I take 2 lines for 1 volt per meter, for 2 volt per meter, it will be 4 lines. Okay, so if the electric field magnitude is more, then the number of lines will be more. Is that clear?
Yes, sir.
So the flux, which is number of lines cutting that area, will be more. So you know the size of the area is more, then the number of lines will be more. Suppose this is the electric field. If you take this area, number of lines cutting this will be less. If you take a bigger area, the number of lines cutting this area will be more. So the electric flux is also proportional to the area. Is this clear?
Yes, sir.
Okay, and it also depends on the orientation of the area. Suppose my area is like this, and suppose I rotate this area like this, then the number of lines cutting through this area will be less.
Yes, sir.
Okay, so it depends on electric field, the size of the area, and also the angle between them. And it depends on the cause of the angle between them. The area vector is defined as normal to the surface. This is the standard convention. The small flat area, if I don't draw a perpendicular to the surface, that will be the area vector. And this is the electric field vector. So when these two are in the same direction, maximum number of lines will cut. And these two are the same direction means theta is 0 and cos theta is how much? 1. Okay, so that's why it goes as cos theta. So this is an example to become clear. I have a square of side 2 meters and the electric field is uniform, 3 volt per meter. What is the maximum possible and minimum value of electric flux that will pass through the square? So this is the square of side 2 meters and the area vector, let this square be in the plane of this paper. So the area vector is perpendicular to this surface, so it will be into the plane of paper. You know this notation, right? For vector, cross means into the plane of paper.
Yes, sir.
Okay, and let me assume that electric field is also into the plane of paper. So here in this situation, maximum number of electric field lines will cut this area, right?
Yes, sir.
Because maximum area is facing the electric field. Suppose I rotate this thing by 90 degrees, it will become like this. Yes. In this case, the number of lines cutting this area will be 0 because all these lines will just touch this surface. This thickness is almost 0. Okay, here in this case, the electric field vector, sorry, the area vector is towards right, and this electric field is into the plane of paper. So the angle between the electric field and this area vector is 90 degrees. And cos 90 is 0. So the flux is E dot dA, that is E into dA into cos 90, that is 0. Right? Is this clear? So when the area is rotated by 90 degrees, the flux cutting through the surface is 0. If I still rotate it by one more 90 degrees, it will become like this. So the area vector, it will come out of the plane of paper. Once I fix the area vector here, I have to keep the same direction. So here, if I assume it's into the plane of paper, here will be out of the plane of paper. So here the angle between these two will be 180 degrees. So cos 180 is -1. So if you include the minus sign, then the flux can also become negative. Okay, so positive flux means the electric field lines are cutting that area, and the way it is cutting is in the direction of the area vector. Here also it's cutting, the number of lines are the same, but the direction in which the electric field lines are cutting is opposite to the direction of the area. That's why it's negative. But the magnitude is same. Here also it's 12, here it is 12, but sign is negative. So the flux can also be negative. Is this clear?
Yes, sir.
So mathematically it's E dot dA. So E into dA into cos theta. So as theta is becoming greater than 90 degrees, it will become negative. Cos theta is positive from 0 to 90 degrees. And from 90 to 180, it's negative. Okay. The electric field in a region is given as E alpha x I cap. Alpha is a constant. X is what? X coordinate. So this is a uniform electric field or non-uniform electric field. This electric field in this question, is it uniform or non-uniform?
Non-uniform, sir.
So if x is 1, it's alpha. X is 2 means it's 2 alpha. So electric field is changing from point to point in space. So it's non-uniform electric field. So total flux passing through a cube bounded by surfaces x equal to L, h equal to 2L, y equal to 0, y equal to L, and z equal to 0, z equal to L. So we should know how to draw this cube. So x equal to L means this is the x-axis. So this point is x equal to L. So we have to draw a plane perpendicular to this x-axis passing through x equal to L. So at any point on this surface, the value of x is same. Is that clear? That's why this plane is called x equal to L plane. You should know a little bit of geometry. You might have done studying in 10th standard. And here it will become part of basic maths. So is this clear? Any point in this plane ABCD will have x equal to L. Is that clear?
That is actually Z only. Z and Y.
Y and Z will keep changing, but the value of x is same, right? See, in 2D,
Yes.
in 2D, x-axis, y-axis, just 2D. Okay, if I draw a line like this, the value of y for all the points in this line will change, but x is constant, right?
Yes, sir.
Similarly, in 3D, I have drawn a plane, but I have drawn this plane perpendicular to the x-axis. So the value of x of all. So this plane I can say x equal to 1 plane, or x equal to L, x equal to L plane. So similarly, what is this plane?
X equal to L.
So similarly, what about this plane? The top one?
Y is equal to 1.
Y equal to 2L, sorry, y equal to L. And what about this bottom plane?
Y equal to 0.
Right. So you got the idea, right? So similarly, the front plane is z equal to L. The back plane is z equal to 0. Okay, so you should know how to draw this cube. Okay, so you have to find the flux passing through this cube, and the direction of the electric field is along I cap. Okay, so flux is basically the lines cutting the plane. So this surface is top one, bottom one, and back one, front one. Is it cutting that surface? It will just touch and go. It will not cut through them, right? Similarly, this front face also will just pass through. It will just touch the surface. It will not cut through the surface. So the only surface it will cut through are the left plane and the right plane. X equal to
But that area vector, we don't know. If you draw that area vector for the plane, then
area vector is, see, for the top, this one, the area vector is outward normal. For a closed figure, the convention is outward normal is the area vector. So for this top face, area vector is outward normal. So the angle between the area vector and the electric field is how much? 90 degrees.
0. So electric field.
Cos 90 is 0. Similarly, the bottom face, the electric field vector is outward, and the front face, the electric field outward is it's in this direction, which is again perpendicular to the electric field. And for the back also, the electric field area vector is outward. So there also the angle is 90 degrees. So this you can understand mathematically, but physics-wise, you just have to think they're just touching the surface, not cutting them. So the only places you cut out the left from the right one. So electric flux to the left face is integral E dot dl. E is along I cap, and dA vector is minus I cap, right? It's outward normal.
Why is that plane?
So it's 180 degrees here, the angle between electric field and the area vector. So cos theta is -1, right? And and alpha x is constant throughout that surface. So x is a constant. It will come out of this integral sign, and integral dA is a total area L square. Just here.
Yes, sir.
Okay, so it's minus L. So with the right one, the electric field value will become 2L, which is alpha into x, the electric field, and x is 2L, and the direction is 0 degrees. Is that clear? Angle between cos theta is cos 0 here. Is it clear? Here there are opposite directions, area vector and the electric field vector. Here area vector is outward normal, same as the direction of the electric field. Right? So it is plus here. Got it? Yes? Is it clear? The mic is off.
Area value changes for right face. It is not L square, no?
No. It's a cuboid. It's a cube, no? Area is still same.
No, that x value changes. No, L and 2L.
Yeah, that's what. This is the x value. 2L. X is a
Okay,
constant.
Q. Okay, that is not Q value. Okay.
X is a constant across this area, so it will come out, but the value of x is 2L.
Okay, cube. Okay, cube.
This point is 2L. Is it clear? Yeah.
X.
So the total flux coming out of this cube is flux coming out of all the surfaces. So the remaining four surfaces are 0. So I just have to add these two faces only. So I have to add these two to get the total flux. Done?
Yes, sir.
Okay. So electric flux through a circular disk. So here there is a charge here, point charge Q, and here there is a disk, and the disk is placed properly in the sense like the center point of the disk and this line and this line and this surface of the disk are 90 degrees. Otherwise, it will become complicated. Okay, if I tilt this disk from this position, then this 90 degrees will change. But I'm placing the disk in a proper way so that it's 90 degrees, otherwise it will become complicated. Now define electric flux through this area. Okay, so if you take a small element, a ring element, so the electric field direction is like this, right? Is it clear? It's radially from this point. I just have to take a small element here that has a point charge. So the force between these two point charges. Actually, here I have to put a unit charge. So the force on this unit charge with this charge will be on the line joining this Q and this small element. That will be in this direction. Is that clear? And this area vector is perpendicular to this one. Okay, and let me assume it's towards right. So this is the area element. So the angle between them is theta. You know how to do complicated integration, or you just leave it because this is you can just remember this result. Do you know to do this sort of integration or not? Okay, I'll just go through it quickly, see whether it's too much for you, then I'll leave it because this may not be required for NEET. I'm more familiar with JE. So E dot dA is E into ds into cos theta, right? Theta is the angle between the electric field vector and the area vector. And the electric field at this point is K into Q by the distance square. This is a constant distance L, and this distance is X. I'm calling it as X, it's a variable distance. So the distance square is X square plus L square. And this ds is area of this elemental ring, that is 2 pi r of dr. So this concept, you know, ds is this one.
No, sir. I forgot it. I have studied for finding gravitational field, sir, but I don't remember it now.
Okay, so this elemental ring, this circumference is 2 pi r, right? That
I
is
guess, sir.
2 pi x. 2 pi x into the thickness is dx. So 2 pi x thickness dx is this small area ds.
Yes, sir.
Okay, and cos theta is x divided by this hypotenuse, that is square root of x square plus L square. So cos theta is this one. Okay, so here the variable is x. Other things are constant. Because I've chosen the ring at particular radius x, and this x will vary from 0 to capital R. Only then I'll be able to cover this entire disk. So x is a variable. Is that clear?
Yes, sir.
So have you used this formula? Flux cutting through this disk is charged by 2 epsilon into 1 minus cos alpha, where alpha is the angle of this cone. Actually, these lines will form a cone. Are you able to visualize that?
What's up?
These electric field lines, which are cutting through this disk, okay, if I take all those lines, it will form a cone. A lot of lines will be inside, all these lines will be inside the cone, but these outermost lines, they will form the surface of the cone.
Yes, sir.
You can visualize that, right? And this,
Yes.
this cone will have a half angle alpha, because full angle means this full angle, that is
Yes,
2 alpha. So a half angle is alpha, so it's 1 minus cos alpha. Okay, you can straight away remember this formula. The flux which is passing through this cone, which is same as the flux which is cutting this disk, is q by 2 epsilon naught into 1 minus cos alpha. Because this integration will be a little bit heavy, I think, for you. It is more for JE, not for NEET. Okay, I'll come back to this later if it is required. Electric dipole, you know, right? What is a dipole?
two equal and opposite charges separated by a distance.
Okay, one more thing is there. The distance should be very small. Okay.
Yes, sir.
Because just separated by a distance means it's like using Coulomb's law. But when when the distance is very small, then we can make some approximations, which will become interesting. Okay, so and we can associate a vector to this thing. So we can define a dipole moment. The magnitude of it is the charge q into the separation. Separation I can represent either by d or 2a. Okay, if you assume this middle point is the origin, the coordinate of this thing will be plus a, and the coordinate of this thing will be minus a. So in that case, the distance between these two will be 2a. So charge into the distance into unit vector. The unit vector is from minus q to plus q. Okay, so this is definition of the dipole moment vector. Charge into separation into p cap, with the direction of the unit vector is from minus charge to plus charge. So when you have a point here, there will be electric field. So we can find electric field with this dipole in two cases easily. So this is the dipole minus q and plus q. So this is the set of points. What are these? These points are called points on equatorial line. This is the axis of the dipole. So along the axis of the dipole, we can get some set of points. Another set of points is in the middle in a perpendicular plane. So this is called equatorial plane. The plane is perpendicular to the line joining the two charges. And along the axis, it's called pointers along the axis. So for these two sets of points, we can find electric field easily. Compared to, suppose I take a general point here, it will be difficult to calculate the electric field. So we will not do that. We'll just only find electric field in this two sets of points. So first do that for along the axis. So to find electric field at this point, I can do by Coulomb's law, or the definition of electric field, and use superposition principle. So the electric field with the minus charge will be 1 by 4 pi epsilon naught. Charge will be the distance square. So distance of minus q from the point, I've chosen the point here on the left side. So this distance is how much?
R plus a.
So similarly, the distance of this plus q from this point where I'm calculating the electric field will be how much?
R minus a.
Yeah. So minus q will be r plus a square, and then q divided by r minus a square. So the sign of the electric field. See, electric field is, I have to put a unit positive charge and find the net force on it, right? So this q will produce a repulsive force in this direction.
Yes, sir.
Okay, and this minus q will create an attractive force in this direction. Okay, so can you see the length of these two vectors? They are not same.
Yes, sir, because of the distance.
Because the negative charge is far away. And another thing is I'm choosing my point here. If I choose a point here, then it will be opposite. Okay, so I'm choosing a point on the left side. That does not matter. The formula will be same. I can choose either way, but I'm choosing on the left side. So according to this thing, the force on the due to the positive charge will be more. Okay, that comes out with this mathematical formula also, because the denominator is small here. So positive term will dominate. So this thing I can Q I can take outside. So this thing I can simplify like this. This simplification is clear. A plus b square and a minus b square, if you add them, the cross term will disappear, only the square terms will remain. Sorry, here there is a minus sign, right? So the square terms will go away, the cross term will be there. The cross term is 2 into a into r, and it will be twice of that. So it will become 4ar, and the denominator is a plus b into a minus b whole square. That is r plus into r minus a, that is r square minus a square the whole square. So this is clear. And then I can combine q and 2a as p, because the dipole moment vector I have defined as q into the separation into p cap, and the magnitude of this p is q into 2a, because magnitude of p cap is 1. So I can combine q into 2a as p. The p is just the magnitude of the dipole moment vector. I have not put the direction yet. So this is clear. Okay, so electric field is a vector, right? Now I can fix the direction. So the direction of this one, direction of p cap is minus q to plus q. So the net electric field will be towards left, right?
Yes, sir.
Which is same as the direction of p cap. So the direction of this thing, this is a positive quantity, and then I put the direction as p cap, and then p cap I can combine with p as p vector.
Yes, sir.
Okay, so I said the dipole will become interesting only if the distance between the two dipoles is distance between plus q and minus q is small. So under this approximation, I can neglect a square term compared to r square. So this will become r cube, cancelling 1r here. Okay.
Yes.
So the electric field due to dipole is 1 by 4% order 2p by r cube. So one way to remember this is, for a point charge 1 by 4%, the charge will be the distance square, right? So instead of charge, we have this vector p here. Instead of r square, we have r cube. And 2 is because along the axis, there are two charges. That way you can remember them. Or you can say the electric field along the axis will be more compared to the electric field along the equatorial plane.
Yes, sir.
So next set of points is on the equatorial plane. So these are the two charges, minus q and plus q. And if you take a point P here, u to plus q will be the electric field in this direction, and minus q will be attractive force, will be in the same direction. So what about the length of these two vectors? Is it same or different? This is electric field with the, see, these are the two charges of the dipole, right? Minus q and plus q. And equatorial is the plane passing in the middle. So if you take a point on this plane, it will be the same distance from both plus q and minus q by symmetry.
Yes, sir.
So this electric field with the plus q, this arrow, and this electric field with minus q. Minus, since it's minus, will be attractive, so it will be towards the charge. So this q will be away from the charge. So what about the length of these two vectors? Is it same or different?
Same.
Why is it same?
Because distance from plus q and to p and minus q to p are equal.
Yeah, and the product of charges, if you just take the magnitude, they are same. It's 1 into q, here it's 1 into minus q, because electric field depends only on the charge. So if I add these two vectors, the perpendicular, the one is along the plane, it will cancel. One is upwards and one is downwards. Those two will cancel. I can resolve these two vectors, one along this perpendicular line and one along the plane. So the one along the plane will cancel, right?
Yes, sir.
So the result will be perpendicular to the plane towards right.
Yes, sir.
Okay, so to get that thing, I have to get the magnitude 1 by 4% cubed by the distance square. So this distance is r square plus a square.
Root of. Yes, sir.
Yeah, and square of the distance is this one. Because the electric field is charged by distance square, right? Okay, and this angle, say it's theta, so it will be cos theta. This component is cos theta. And two of them, why is this 2 is there?
Because 2 times.
Because this component is also there. One component is because of plus q, other component is because of minus q. And see, this angle is theta. What about this angle?
Which one, sir?
This angle is theta with plus q. What about this angle? It's also theta by symmetry, because both plus q and minus q are equidistant from this plane, and this point is also equidistant. So if it is theta, this also should be theta, right?
Yes.
By symmetry, because it's just passing in the middle. And so this theta is the angle between horizontal and this line. So this is also horizontal, right? Parallel to the horizontal. So this angle is also theta.
Yes, sir.
And this angle is also theta. By symmetry, you can say, if this thing is so
Internally opposite angles.
yeah, you can say that. So this, you get this one, and you can combine q and 2a as p. So you'll get this one. Again, you have to use that approximation that a square is small compared to r square. So it will become like this. So to remember this thing, electric field is 1/4 of the charge divided by distance square for point charge. For a dipole, it becomes instead of r square with r cube. And the direction here, p cap direction is from minus q to plus q. It's towards left. This is the direction of p cap, right? The direction of electric field is towards right. So that's why it's minus p. Here I'm just getting the magnitude. Okay, and direction I'll put it as minus p cap, and minus k cap into p will become minus p. This minus sign is clear?
Yes, sir.
Here I'm just getting the magnitude. After that, I fix the direction by this physics argument. Okay.
Yes.
So the difference between this and this thing is, here there is a factor of 2. Okay. Here there is no factor. The way to remember is electric field along the axis will be more, because here the two vectors are parallel to each other. So the full vector will add or subtract. But here in this case, the electric field components, one of the components is getting wasted. Only the cos component is getting added. So that's why the electric field is less here. Just for remembering the formula I'm saying. Okay.
Okay.
And direction you can fix by physics. Okay. And actually, dimensions wise, Q has got a length dimension, because it's P is Q into the separation, right? Q into 2A. So the dimension of P is charge into length. So that length will cancel with this one of the length here. So the full thing, the dimension is charge by r square, because the dimension of electric field cannot change.
Yes, sir. Yes, sir.
Okay. Another way to remember why this cube is, there is a length dimension here. To cancel this thing, there has to be a cube. Just for remembering the formula I'm saying.
Yes, sir.
Okay. When I put a dipole on a uniform electric field, force on a charge placed in external electric field is QD. Okay. And for this minus Q, it's minus QD, and the direction of minus QD is opposite to the electric field. Here I mean the electric field direction is vertically upwards. Okay. So the direction of force on plus Q is upwards, and minus Q is downwards. Is that clear? Direction of I cap and minus I cap are opposite. So direction of E and some negative quantity in E will be opposite. The direction of forces is Q and minus Q are opposite. Is this clear? Yes?
Yes, sir. So that E is already present.
See, even if you think mathematically, Q is a positive quantity. So for example, say Q is 2 coulombs, okay? And the charge of this thing is minus 2 coulombs. So this force is minus 2E, and this force is 2 into E. So if the direction of 2 into E is positive upwards, The direction of minus 2 t will be downwards. What is the confusion?
Sir, that E is already present, right? It is not due to the charge is present there.
No, E is
That is
external field. It's already present.
okay.
External.
Okay.
Some other source charges are there. So you don't have to bother about that. You can just assume this, there is a big, huge capacitor plate here and another capacitor plate here, which will produce this field. And this capacitor plate has to be positive, right? And this has to be negative. Okay, and this is positive charge, so it will attract it will be attracted towards the negative plate, and this is a negative charge will get attracted to the positive plate. So that also you can fix the direction. Is it clear?
But if I reverse the charge of the capacitor plate, then it will be
No.
opposite.
Yeah, if you reverse, but the electric field direction is fixed, no?
Okay, okay, yes, sir.
Okay, to get this electric field, the capacitor plate has to be like this only.
Yes, sir.
And it's external, it will not nothing to do with these charges. Okay, so if you take the whole thing as a system, what is this? What are the net force acting on the system? Have to add these two forces, right? I'll consider this whole thing as a body or a system. So if we just take this body as a full, one force is acting here, which is upwards, another force is acting here, which is downwards. So sum of these two forces will be what? Is it clear?
Yes, sir.
Okay, but the force, if there is a rigid body and if the forces are acting in two directions, 2 points, net force might be 0, but it might produce a rotating effect. So this force will try to rotate this body in this direction, right? And this force will try to rotate this body in this direction. So both the forces are trying to rotate the body in the same direction. So both this rotating force, or it's called torque. Okay, this torque and this torque will
So
get
why
back.
is this turning effect happen, sir?
See, if the charge of this Q, it will have some mass, right? So let me assume both are equal masses, M and N. If you have a body, if I try to apply a torque, it will try to rotate about its center of mass. That's a basic concept. And the center of mass here is in the middle, right? This is center of mass. See, if you
Yes,
have
sir.
just a minute, if you have a rod like this, say this is uniform rod, the center of mass will be here, right?
Yes, sir.
If you try to apply a force like this, how it will rotate? Anti-clockwise. Yes?
Yes, sir.
And if I try to provide a force at this point like this, because of just forget this force, only because it's left force, we'll try to rotate this way. So these two torques will add. Force will give rise to the torque if it is at this distance. Okay, so these two torques. So the same thing is happening here. One, the force is upwards, so we'll try to produce this anti-clockwise torque, and this force is also produce an anti-clockwise torque. So both the torques will add. And torque is given as the force into the perpendicular distance. So this is the force and the perpendicular distance of the force. This is the perpendicular distance. And this is A. And this is 90 minus theta. So this distance is A sine theta. So the perpendicular distance is A sine theta.
So 1 second, can you please tell me how do you take the A sine theta?
Torque is given as what?
4 R cross F.
That is R into F into sine theta, right? Because theta is the angle between R and F. So here, F is in this direction, vertical direction, and R is this one. So R sine theta.
So that A itself is If it's a perpendicular direction only, no, why are you adding that sign?
No. This is not 90 degrees. See, Q is vertically upwards. So with the horizontal, it will be 90. This is it's at an inclination. This line is not horizontal. Okay. So if you take this angle as theta, this is 90 minus theta. So this I can write as force into r sin theta is r perpendicular. The direction between perpendicular distance from the force vector. So this is the force vector. So from the force vector, the perpendicular distance is this one. That is a sin theta. Because this angle is 90 minus theta. So a cos 90 minus theta is a sin theta. This perpendicular distance. So similarly here, this force is this way. And this perpendicular distance is a sin theta. You can just take it as by symmetry. This angle is 90 minus theta. So this perpendicular distance is a sin theta. So both the torques are, so it becomes 2 times QE into a sin theta. And Q to E I can combine as P. So it becomes P sin theta. So in vector form, I can write as P cross E. And P is from minus Q to plus Q. So here the direction of P is this way, P cap. Or we can also say P. And the direction of electric field is upwards. So P cross E will be out of the plane of paper. So the direction of torque is, when you have out of the plane of paper, it's anti-clockwise torque, right? That you can get by thumb rule. I have to put the thumb in the direction of the torque, and the direction in which the fingers curl is the direction of the rotation. So this direction is correct. Is this clear? For anti-clockwise torque, the thumb will point out of the plane of paper. Here it's anti-clockwise torque, so the direction which is called by P cross E is correct. So torque on a dipole which is placed in uniform electric field, because the electric field at plus Q and minus Q are same.
I cap cross or J cap will be minus K cap minus.
No, don't have to take I cap.
P is in which direction, sir?
I have drawn here minus Q to plus Q.
It is I cap or
not I cap. It's at an angle, no. So if you define, you don't have to do that, no. If you take this as x-axis, horizontal is this one, but x-axis is at an angle. If you want to define as I cap, you don't have to do those things, right? Just think of the terms as a vector only.
Okay.
P and then E is vertically upwards. So P cross E is this angle. Okay, so that will give me a direction like this out of the plane of paper. That means the torque is anti-clockwise. That can be got by thumb rule. Thumb should point in the direction of the torque vector. So the fingers will curl in the anti-clockwise direction. So everything is correct here. Okay. So now potential energy of a dipole placed in a uniform electric field. So when something has acquired potential energy, then it has got some energy, which will do some work. So if you have a system, if you do work on the system, the potential will increase or decrease.
Sorry, sir, what?
Okay, I'll repeat. Say, let me take a simple case. Say a body here. Okay, let it have some mass. I'm doing some work on it. Work is done on M. So the potential energy of M will increase or decrease. This is basic concept. Sorry? Increase.
On that body.
Yeah, on. Okay, the way to remember is if the body is doing some work, it will lose energy, right? So potential energy will go down if it does some work. But if the external agent is doing work on it, then its potential energy will increase. One easy way to remember is, suppose this is the Earth's surface. I have a mass here. So say I'm taking the mass and putting it here. Okay. To do that, I have to do some work, right? I have to lift it and put it there. So I'm doing some work. So I'm doing some work. The potential energy of this one is what? mgh. Initially, the potential energy was 0. Now it has become mgh, right?
Yes, sir.
So that's because I've done some work to lift it and put it here. That work is done by me. I'm external to this mass. So when an external thing does work on the body, then its potential energy will increase.
Okay. Sir,
Yeah.
so that potential energy lost by you will be equal to that potential energy gained by that body. Yeah.
What?
So you have to do some work to keep that body on that rod, no, sir?
No. Okay, we'll come to that.
Okay.
Let me get rid of this one. Okay, first get the basic idea of potential energy. Whenever you do some external work, when an external thing is doing work on the object, the thing will potential will increase. Okay, here the external thing is the electric field. Okay, so the electric field. Okay, electric field is present. Suppose I try to rotate this dipole. So because of the electric field, there will be forces acting like this, right? F1, F2. Since it's uniform, both F1 and F2 are same magnitude, but the directions are opposite. So suppose I try to rotate this dipole in this direction, anti-clockwise. I have to do some work, or I don't have to do any work.
You have to do some work.
So when I try to rotate this dipole and the dipole becomes like this, then the potential energy has to increase.
Yes,
Okay. So just follow this one. To rotate the dipole with small angle d theta, and okay, external work is done by external agent. Okay, and the work done is torque into d theta. In terms of linear motion, the work done is F into ds, right?
Yes, sir.
For a rotational motion is, instead of F, it will be torque, and ds will become d theta. So rotational work done is torque into d theta, and torque is P cos E, that is P sin theta into d theta. So this is the work done that will going to increase the potential energy. So by energy conservation, increase in energy is the work done on the system. There are no other forms of energy. Okay, so increase in potential energy is the work done on this rotating this dipole. And suppose I rotate this dipole from this position, suppose let the dipole be initially here, be like plus q is here and minus q is here, and whatever is shown is the intermediate position, and finally I get the dipole here in this vertical direction. So the total work done will be from, okay, I'm not going from 0 to, so okay, I'm rotating from theta to 90 degrees. Okay, this is the starting position, and final position is 90 degrees, like this. Angle is measured from the horizontal, that's with respect to the electric field. So when I do this thing, the total work done is this elemental work done. I have to indicate from theta to 90. That will be the increase in the potential energy. So final potential minus initial potential energy. Is this clear?
Yes, sir.
So integral of sine theta is minus cos theta. Okay, and I have to put the limits. So if I put the limits, I'll get this one. Cos 90 is 0. Okay, so this I can write as P dot E.
Yes, sir.
Okay, and this potential energy at 90, I can take it as reference. Whenever I have a potential energy concept, I can always choose a reference and make the potential energy at that point as 0. So here, in this case, at 90 degrees, I take the potential energy as 0. So from this, I get u theta as minus P dot E. This is an important question you have to remember. So from the mathematical, this is also P to E cos theta. So this thing will become 0 when theta is 90 degrees. So the reference is theta equal to 90 degrees. So one formula is,
Minus 2 that.
no, this step is clear, no? So then you have to put the limits. Integral of sine theta is cos theta. Variable is theta. Other things are constant.
Yes, sir.
So those things will come out. So integral sine theta is cos theta minus cos theta. So you can put the limits, right? This minus sign you can absorb in this limit and interchange the limits. So it will be cos theta minus cos 90. Cos 90 is 0. So this one.
And that will be minus P cos theta only. So why taken out that minus one?
No,
Second
minus.
step.
Okay, minus, and then you have to put the upper limit, right? Upper limit is what? Cos 90 minus cos theta. Cos 90 is 0. So minus cos theta, and this minus will become plus cos theta.
No, it is minus was not present from the first no, sir.
Integral of
Second
sine.
step is,
No, this minus is clear.
and this one. Then the third step also minus will come, no, sir.
No, you have to put the upper limit first, right?
No, after simplifying one, you have written that as minus P cos
Yeah,
theta.
I have skipped a step. I have skipped one step here. So if you write the step, it will become
P cos theta.
cos 90.
Simply P cos theta, sir. Why you have written that minus sign?
Hold on, hold on. So this step is clear. Minus, I've kept it minus. I have to put the upper limit, right? Cos 90.
Okay,
Then-
for sin theta, integration of sin theta is minus cos theta.
Yeah.
Okay. Okay, yes, sir.
See, derivative of cos theta is what? Minus sin theta, right?
Ah, yes, sir.
So in the reverse direction, integral of sin theta will become minus cos theta.
Yes, sir. Yes, sir. Yes, sir.
So now it's clear. So this is the
Yes,
result. So this is the result you have to remember. Potential of a dipole in the electric field is minus P dot E, and the reference is theorem 90. That will automatically from mathematics because it's P into E into cos theta. Cos theta will become 0 at 90 degrees. So when the dipole is perpendicular to the electric field, it is considered as zero potential energy. So these are two formulas for the dipole in uniform electric. One is the torque P cross E, and the potential energy is P dot E minus P dot E.
Why, sir, that why you have included that minus sign in the final expression?
Here there is a minus sign. No, U90 is 0. I'm taking the 90 degrees as a reference. At the base, the reference for potential energy is 0. So this minus sign is there. That will come here. Okay. Okay, and one more way to understand this minus sign is, see the potential energy at this place, say U1, and the potential energy here, U2, where the potential energy, U1 is more or U2 is more?
U2 is more.
So U2 is greater than U1, right? And what about U3? It's more than U2? Yes?
Yes, sir.
Okay, so if I don't put this minus sign, here it will be 0, here it will be some positive, say 5, here will be, sorry, what am I doing? Here will be, okay, here it is 0, and here the potential energy should be less than this one, right? So you have to put P dot E. So, okay, P dot E is here 0, right? And here it should be negative because here the potential energy is less than that one. So it will be some negative 2. Here will be some minus 5. This, for example, I'm saying. Because here the potential energy should decrease, no? So if this minus sign is not there, then it will not be satisfied.
Yes, sir.
Right?
Okay.
Okay. Dipole is an equilibrium force and torque on it is 0. For a particle in translation motion, it's called its inequilibrium, the net force is 0, right? But if you take a rigid body, which has got a tendency to rotate, for it to be in equilibrium, both the force and the torque should be 0. Okay, so for a dipole in uniform electric field, what are the equilibrium coefficients and what are the corresponding values of theta? And you have to say whether the equilibrium is stable or unstable equilibrium. So if you take a dipole placed in uniform electric field, the force will be plus QE and minus QE, right? So the net force is always zero. Is this clear?
Yes.
If you assume E is uniform, we are not complicating the situation, we are assuming E is uniform. But the torque is not zero because torque will be in the same direction. This plus Q will have a torque in this direction, and this minus Q will have a torque in this direction. So these two torques will add. Okay, but at one particular position, the torque will be zero. The torque at this point will be zero, right? Suppose the dipole is like this, say minus is here and plus is here. Torque at this position is zero, it's P cross E. Is that clear?
No, sir, I don't get it.
Okay, you can also understand the physics. If there's a the plus charge here, the force on the plus charge will be like this, right? Q into E, and the force is minus charge will be in this direction, Q into E, and this is the center of mass, right? So I have two forces which are passing through the center of mass, so it will not produce any torque. Suppose I have a rod like this, and the center of mass. If you have two forces like this, equal forces, will you rotate this rod?
No, sir.
So that's what is happening here. When the dipole is like this, it will pull in the opposite directions, and the force vector is passing through this point. So here the torque will be zero. And if the thing is like this, plus on the left side and minus on this side, then the direction of P is towards left. So here the forces, here also the force will cancel. Electric field is towards right now. So here the force on this thing will be like this, and here the force on this thing will be like this. So these two forces will cancel. It will not create any torque. Force will always cancel, but it will not, the torques will also cancel in this position. Okay, so these are the two positions for which the dipole is in equilibrium.
Yes, sir.
Okay, so this plus Q, if we rotate it like this, plus Q will come here, minus Q will come here. So that is this situation. If we rotate it fully like this, then it is this configuration. So for these two configurations, the net torque is also zero. So theta equal to 0 and theta equal to 180 degree are equilibrium positions. So, and what is going to be stable equilibrium?
It is like in U-shaped platform. If you put on bar.
This is stable, right?
Yes, sir.
This is unstable. If we give little bit disturbance from this point, it will come back to this origin position. Here, if we give a little bit disturbance, it will just move away. So it's an unstable. So when the dipole is like this, say plus Q is like this. Suppose if we give it a little bit push like this, plus Q. So will it come back or not?
Sorry, sir.
See, plus Q is here and minus Q is here. This is an equilibrium position, right? Suppose I give a slight push like this and make the dipole like this. Will it come back to its original position or not?
Yes, sir.
Okay, because the torque is clockwise. So the clockwise torque will bring it back to the original position. But here, if I try to displace it like this, the torque is clockwise, right? So it's still further move it away. Is that clear?
Yes, sir.
Okay, so theta equal to 0 is stable. Theta equal to 180 is unstable.
Why that particular 180 degrees, sir? Why?
Theta equal to 180 means minus Q will be here and plus Q will be here, because the direction of P vector is from minus to plus, right? And electric field vector is towards right. So the angle is what? 180 degrees. Is this clear? Yes. Yes or no?
And that angle is 180 degrees, sir.
You are asking why is it 180?
No, no. If it is at 180 degrees, means why it will not come back to its origin?
Yeah. See, 180 means plus Q is this one, right? And this is minus Q, right? Yes or no?
So can it
Okay, actually no, minus is here and plus is here. Okay, so now if we try to rotate this plus Q like this, will it come back or not? Because torque is clockwise.
Okay.
So the clockwise torque will still take it further away. So it will not return back.
Yes, sir.
Here, if I try to displace it a little bit like this, the clock is clockwise. So it will try to bring it back here. Clock is always clockwise.
Okay.
Okay, so and torque is P cross is P into E into sine theta. So this torque is uniform or non-uniform?
Non-uniform.
Because theta is going to change, right? From point to point. And where is it maximum?
90 degrees.
So torque is maximum here, and here the torque is 0.
Yes, sir.
Okay, so you can understand physically as at this position, this force vector is at farther distance from the axis, you can see axis of rotation. Okay, so this distance of the force from the point of rotation is going to increase if we're increasing theta up to 90 degrees. Okay, so if you make it like this, the electric field vector here, then this distance is small. So the torque will be small. So maximum torque is in this position. Okay, so the torque is a sinusoidal function of theta. Similarly, the potential energy, which is P dot E, it's also function of theta. It's also non-uniform. Okay, and where is it maximum potential energy? When cos theta is -1, right? Because already minus sign is there. Cos theta will go from -1 to +1. So when cos theta is -1, it will cancel this minus and will be the maximum. So potential is maximum at 180 degrees. Is this clear?
Yes, sir.
And minimum at 0 degrees. And potential is maximum should be unstable, right? That is the potential energy concept.
Yes, sir.
So 180 degrees is this location here. So it is matching with this understanding in terms of torque. Okay. Okay. So we'll close now.
Okay, then bye.
Okay. So this notes is already with you. If you
Yes, sir.
read the notes before coming to the class, we can go faster because we have to. Not much time is there, no.
Yeah, but I'm reading electrostatics also.
Okay. So tomorrow we'll meet.
Fine, sir.
Okay. Bye.